Hello, assalamu alaikum everyone. So this is the 14th lecture of the course, and this is the second part of wireless sensor networks, so medium access control protocols. Okay, so we're going to learn a few more protocols related to wireless sensor networks. Let's move on. So the first protocol that we're going to learn is BMAC, okay, or Berkeley MAC. So it was proposed after SMAC or sensor MAC, which we learned previously, and it included a few more modifications compared to SMAC. So SMAC used RTS and CTS or handshaking protocol to start its communication, as you already know from the previous slides or previous lecture. So instead of RTS CTS, BMAC uses CSMA or carrier sense multiple access. Okay, so we're going to see it in details. For now, let's move on. So motivated by the need to monitor applications, BMAC was proposed because it can sense the channel. As a result, it can monitor various applications and nodes, but it can also provide other services because it's very flexible. So other services include target tracking. That means tracking of moving nodes maybe, or moving vehicles even, or moving any object. So localization, triggered event reporting, and there are many more things. So it employs an adaptive preamble sampling. Okay, so you know what preamble is, but what is adaptive preamble sampling scheme, right? So we'll see that when we see the procedure details. So it uses this procedure to reduce duty cycle and minimize idle listening. Okay, so duty cycle means the amount of time it needs to be awake, or a node needs to be awake. Okay, so it reduces that time in order to achieve low power operation. So as I have said, it uses CSMA, right, carrier sense. And if you remember, in WLAN, the carrier is sensed using clear channel assessment, right, CCA. So this is a figure of how it works. So the top part is the received signal strength indicator, or RSSI, which you already should be familiar with. Okay, and I'm going to explain a little bit about this figure. So this is the signal which is received from a CC1000 transceiver, and as you can see, it's at the beginning there was only noise, and this is also noise. Okay, and just between, let's say, 22 milliseconds to 54 milliseconds, you can see that a raise in the power level has been detected, which means someone is actually sending a packet, right? And this is actually true because during that time the transceiver was used to send the packet. Okay, so when thresholding was done, so something like this was got. Okay, so you can see a bit ups and downs here as well, but only when the packet is being sent is a constant down. That means the channel is busy. Okay, and during this time the ups means that channel is free. Okay, so after that, when it is converted to something like this, which means it is converted to only, this one was converted to zeros and ones, and this is converted to, let's say, outliers. Okay, or to receive outliers, or to detect outliers. Okay, so this is the only outlier that is present, and otherwise we can see that it is a clear indication of when the data packet was sent. Okay, so this is sort of how clear channel assessment works in case of BMAC. So the procedure is, it wakes up from sleep at the very beginning after a timer interrupts. That means it has a duty cycle timer, right? So it has fixed duty cycle. So at the start of the duty cycle, when the timer interrupts the sensor node, it wakes up from sleep, and then it starts configuring the radio and commencing the startup phase. Okay, so turning on the radio requires a bit of time. So upon stabilization of crystals oscillator, okay, so you might already know this, but let me again go through this. So crystals, when they vibrate or when they oscillate, that's how actually the radio frequency waves or electromagnetic waves are generated. Okay, so upon stabilization of the crystals oscillator, which is used to send the data, or which can also be called the radio, now it enters the ready to receive mode. Okay, so switching from this crystal oscillator stabilization to the ready to receive mode also requires a little bit amount of time. So once it's ready to receive, it performs ADC acquisition. Okay, ADC means analog to digital conversion. Okay, and acquisition means a specific amount of signal is received only for sampling. Okay, so it analyzes that sample, and it turns on the radio first. Okay, so it turns on the radio, it receives a sample message, then it turns off the radio and then it starts analyzing the sample signal that it got. Okay, so after analyzing that, it starts on the LPL mode. Okay, or you already know what LPL mode is. Okay, so during this time it only analyzes the channel to see whether there is an activity or not. Okay, so during this time it is not ready to receive. Okay, so this is not the ready to receive mode, rather it's a very low power state where you can only sense the energy level of let's say the channel. Okay, so if there is no activity, then the node again goes back to sleep. Okay, so this is showing the procedure using time as x-axis, and as y-axis it shows the current that is received by the sensor node. Okay, so let's go through this. At the very beginning it was at sleep, so when it's at sleep, then there is no current. Okay, because it is not receiving anything, so the energy level inside the sensor node is 0 or close to 0. Afterwards, when it initializes the radio, it is still not receiving any packet. Okay, so this current change is due to the internal mechanism of the node itself. So this is the part where it's initializing the radio, and then it starts to stabilize the crystal. Okay, so after stabilization is done, as you can see in here, you can see that it raises a bit, so it's still not stabilized, and after it's stabilized, then it is ready to move into ready to receive mode. Okay, so the time that you see here, okay, so Rx, this Rx is actually the Rx means receiving, right? If you remember, TX means transmission and Rx means receiving. So Rx is the ready to receive mode, and before that is the switching time for shifting from the stabilization of the crystal to the ready to receive mode. And so after that it does the ADC sampling. Okay, and then it goes back to sleep. Okay, so when it's asleep, that is the time when it analyzes the sample that it got. Okay, so why do we need this sample? We need this sample to understand the noise level. Okay, so that afterwards when we receive a packet, we can compare that with the noise level to understand whether we are actually receiving a packet or is this only a noise. Okay, so this sampling is done to get a reading of the environment. Okay, so next we are going to move on to another protocol, which is LEACH, or low energy adaptive clustering hierarchy. So this is a TDMA, or time division multiple access based MAC protocol. So the procedure is it lowers, or the motivation is actually it lowers energy consumption required to create and maintain clusters in order to improve the lifetime of a WSN, or wireless sensor network. So as you can clearly understand that it maintains clusters, right? So whenever there are concerns of clusters, that means there has to be a central node which sends a message, right? If you remember, we studied two types of architectures in WSN. One is clustered architecture and another is layered architecture. So in case of clustered architecture, there has to be a cluster head, right, which sends the message. So this protocol, it sort of tries to reduce the load of the head so that the lifetime of the wireless sensor network can be improved. So prerequisites for implementing this protocol is it has to be a dense network of nodes, and there has to be reporting to the central sink. So that means there has to be a central sink present within the proximity of the cluster so that they can send the message directly to the sink. So each node should be able to send message directly, not only the cluster head. Okay, this is a special requirement only for LEACH. So the normal nodes, they should also be able to send message or send signals to the sink. Okay, so the idea is it groups nodes into clusters, which is pretty obvious, and each of these clusters are controlled by cluster heads. So in each cluster there will be only one cluster head. So there are two phases. The first one is the setup phase. So during the setup phase, the clusters and the heads are set up, which means the clusters are formed. It is determined which node will be inside which cluster, and the heads are also determined. That means who will be the cluster head of each of those clusters. Okay, and once all the setup is done, then starts the steady phase. So in the steady phase or steady state phase, the data transmission starts. Okay, and this is continued for a specific amount of time. Okay, this which is called a round. Okay, so the total time that the steady state remains along with the first setup phase is called the round. Okay, So about 5% nodes become heads, depending on the scenario. Obviously, depending on the scenario, the percentage might change, but in general we can say that for each round about 5% nodes become the cluster heads. So you can understand that that means you can actually find out the amount of clusters that are formed, right? Okay, so cluster heads are changed through rotation. So once a round is finished, then another cluster head is selected, and then again a round starts. So for each round, that means for each setup phase and steady state phase, there will be a fixed number of cluster heads. Then again for the next round, other cluster heads will be selected. So in this way, actually the energy or the lifetime is improved, because all the load is actually distributed throughout the cluster, instead of only one node going through all the pressure of being the cluster head. So this is how actually the lifetime is improved. So the cluster heads at the very beginning advertise themselves. Okay, so there is a random algorithm or stochastic process, you can say, to determine the cluster head. Okay, so that stochastic process, you can actually study it yourself, because it will take a lot of time to explain, but that is also very interesting, and I have provided the reference at the end of this slide, so you can study the paper yourself. But what that stochastic process does is, let me explain in short. So at the very beginning, it assumes that all the nodes have equal probability of becoming cluster head. Okay, so then each node implements a sort of randomization, and if it selects itself as a cluster head, then it knows that it has to advertise itself as the cluster head. Otherwise, all the other nodes who are not able to become the cluster head, they will not say anything. So only those who got selected as the cluster head randomly, they will advertise themselves at the beginning of the round. Okay, so once the advertisement is done, all the other nodes then will join the strongest signal. Okay, so of course there might be one, two or more cluster heads within the proximity of a single node. So it will detect which cluster head has the strongest signal, and then it will join that cluster head. Okay, so now one important thing here is, after the first round, the number of cluster heads that were already selected, they will not stand for the cluster head again. Okay, so in the next time, the stochastic process will be a bit changed, so that only those 5% of nodes are not selected again, and within the rest 95% nodes, again the algorithm will go on. Okay, so this goes on until almost everyone becomes the cluster head at least once. And once this is done, it starts again from the beginning. That means now everyone again has the equal probability to become a cluster. Okay, so this goes on for each round. So what happens in the steady state? In the steady state, the heads collect and aggregate data and send it to the sink. So that means the heads receive data from all the nodes in that cluster, and then it compresses the data, or performs some sort of aggregation, so that it does not have to send all of the raw data. It sends only compressed data directly to the sink. Okay, so you can think of it sort of like a software defined network as well, but instead of defining it by software, it's only the presence of a cluster and a cluster head. So the cluster heads organize both how the cluster's heads will communicate with the sink, and also how the normal nodes in the cluster will communicate with the cluster head. So CDMA, or code division multiple access, is used for head to sink transmissions. Okay, because we know that the head to sink transmissions will be very less. Okay, they will be only done let's say after a huge amount of time, right? So we can use CDMA here, and which is actually what the heads do. And TDMA is used within a cluster. So TDMA, or time division multiple access schedule, is used when the normal nodes communicate with its own cluster head. Okay, and both of these are organized by the cluster heads themselves. Okay, so this is actually the figure of the procedure. So at the very beginning, you can see the self-election of cluster heads. Okay, so this is where the randomized selection procedure is started in every node. So every node selects a random number, let's say, and determines whether that random number lets the node to be a cluster head or not. Okay, so once that randomization procedure is done, then those nodes who have selected themselves as the cluster heads do an advertisement phase. Okay, and during this advertisement phase, CSMA is used to send packets or broadcast messages and advertising themselves. So after that, the cluster setup phase starts, where each of the members compete using again CSMA, so that they can join or communicate with the cluster head to select that as their cluster. Okay, and after that, once the setup phase is done, the cluster setup phase is done, then the schedule is broadcasted by the cluster heads. Okay, so after the schedule is broadcasted, now the nodes also know when they will be able to send data to the cluster head, and the CDMA is already fixed by the cluster heads themselves. Okay, so then the steady state starts, and the steady state sort of goes like this. At the first time slot, the nodes will be sending data, then the second node will be sending data, and so on up to the nth node of the cluster can send its data. And afterwards, again it will start from the first time slot. Okay, so this cycle goes on for a fixed amount of time. So this fixed amount of time along with the setup phase is called the fixed length round. Okay, so that was another protocol. Now we are going to start receiver initiated MAC, or receiver initiated medium access control. Okay, so this is the last protocol that we're going to learn in wireless sensor networks. Okay, so all the protocols that we've learned till now, they're actually pretty old, but they're the foundation of wireless sensor networks, and they have many citations. You can see some are having, let's say, 19 to 20,000 citations, and the minimum is for each of these papers about 7,000 or 8,000 citations. Okay, so these are the foundations of the network protocols, and even now some protocols are changing, LEACH for example, or SMAC maybe. Okay, and changing those protocols and improving them, but these were the foundations. Okay, so let's move on. So for the motivation for receiver initiated MAC is the receiver of a data packet is the point of interest. Okay, so that which is actually true in case of wired networks. It is very easy to detect a collision because the state at the receiver and the state or environment at the sender is almost the same. But in case of wireless networks, the state or environment in the receiver's end is completely different, or might be completely different compared to the sender. So it is very difficult for the sender to understand whether there is a collision at the receiver or not, which is one of the prime problems of a wireless communication. So the receiver of a data packet is actually the point of interest. So if we recast the collision avoidance dialog, so that the receiver, sender or both can have control of the dialog, right? So that means that if you want to if you remember, there are some dialogues related to collision avoidance, right? For example, RTS, CTS. So the CTS is sent by the receiver as well, so that the condition of the receiver can also be understood, right? And both the sender and the receiver have control over the dialog. So this was one solution, but the target of RI-MAC is to provide equal or better throughput than any sender initiated IEEE protocol, for example 802.11, because RTS is initiated by who? The sender, right? So compared to that, what RI-MAC does is the procedure is actually started by the receivers instead of the senders. Okay, so now what we're going to do, instead of using the senders to start the dialogue or start the communication, the receivers will start the communication, which is why the name comes receiver initiated MAC, or receiver initiated medium access control. Okay, so the issues which arise in case of receiver initiated protocol is we do not know when to poll, because usually when someone has data to send, only then it starts polling, right? But now only then it starts sending data. But when we are polling, that means now we are the receiver. We do not know when to poll, or we do not know when the sender has any data to send. So that's the first problem. The second problem is to whom. So as I'm the receiver, there are many nodes who can be the sender. I don't know who the sender is. So we have to also decide to whom we will be polling, whether the poll will be sent to a particular neighbor or to all the neighbors in a broadcast way. Okay, so for dense networks this is very difficult, because you cannot broadcast or you cannot actually create a schedule very easily, because there are many number of nodes which can actually be a potential sender. So the third problem is how. So whether the polling packet asks for permission to transmit, just like RTS and CTS. Okay, so these are the three issues which arise when we use polling for RI MAC. So this is actually a protocol which is quite well known, which is MACA. Okay, so what or let me just call it MACA. So MACA uses a ready to receive packet or RTR packet, which says that okay, now I am ready to receive a packet. Okay, so this is called MACA by invitation or MACA by. Okay, so this is one procedure which this paper also uses. So a polled node can send a packet to the polling node or to any other node, and the remaining nodes hear the RTR and they back off. Okay, so they assume that I cannot send any data, but this does not avoid collision. Okay, but this can be a process. So this paper actually proposes receiver initiated medium access or REMA protocols. Okay, and there are actually two types of protocols here. Okay, we are going to go through them. So what it does, it does polling by the packet that we already explained earlier, ready to receive packet or RTR packet. Okay, and it also uses carrier sensing before sending. So whenever it senses the channel to be free, only then it sends an RTR or request to receive. So there are two types of protocol here. One is REMA SP or REMA simple poll, and REMA DP or REMA dual poll. Okay, so a simple poll receiver initiated protocol means that the polled node can only send data to the polling node. Okay, that means let's say I am the receiver and I am sending a poll, then only the sender can receive the packet to me. And compared to that, REMA DP or dual poll means if I am the receiver and I initiated the communication, then I can also send data to the sender. Okay, so this means that REMA DP can send two data packets at the same time, during which REMA SP can send only one data packet. Okay, so next we are going to see these two protocols in detail. But before that, I think I'm going to stop here, because some students have said that if the videos are shorter, it will be easier. So I'm going to break this lecture into two smaller sub parts, and I'm going to end this part here. And in the next part, we're going to see REMA SP and DP in detail. So with this, I'm going to end the lecture here. Assalamu alaikum everyone.